So this video lesson is going to deal with Hess's law, which is section 5.7 in the textbook. However, before we go to section 5.7, I would like you to take a look back at section 5.4, where you see the phrase state function. Okay, so this is on page 5 in our current notes. So take a moment and look there first, because this idea of a state function actually applies when we talk about Hess's law. So let's start with that. So first off, what is a state function? You see the definition right here. It's a property that depends only on the present conditions. In other words, it doesn't matter how you got there, or we could say that that's path independent. Okay, now what does that mean for something to be path independent? Let's talk about some general examples first, and then we'll talk about how this applies to enthalpy. So, first off, if we look at our image right here, you can see this is Mount Everest. So you could see one option would be to take the helicopter from base camp here all the way up to the summit. Okay, so that distance we see there in blue. Option 2 would be to actually hike Mount Everest. So you can see that here with all the different camps along the way to ultimately get to the summit. Okay, now if we were looking at the net or overall change in elevation, even though these two paths, the blue and the red, are very different, the overall change in elevation will be the same from here to here, whether you took the blue path or the red path. So we could say that this, in this case, change in elevation is a state function. It was independent of the path. You still only cared about the initial and the final conditions. So there's one example. Another example is what you see right here, the net caloric intake. So the average required recommended, I should say, calories for, an average person is about 2,000 calories per day. Now, whether you take in those 2,000 calories by just eating carefully and making sure that you only take in 2,000 calories, that was one way to do it. The other way would be to eat more than 2,000 calories, but then exercise to burn off some of those calories. So, either way, whether you dieted and ate carefully or whether you ate normally and then exercised, you could still have a net caloric intake of 2,000 calories per day. So, again, the path does not matter. Whether you ate carefully or exercised extra calories off, you still would see that the initial and final values are all that mattered. Okay? So how does this relate to Hess's law? Well, what we know is that enthalpy is actually a state function. So what does that mean? That means that when you're dealing with energy changes in a chemical reaction, the overall value is all that matters from the beginning to the end. It doesn't matter what the path was you took to get there, okay? So keeping that in mind, now let's skip ahead to where you see section 5.7 and the heading Hess's law. All right, so section 5.7, Hess's law. Here's the statement of Hess's law. So if a reaction is the sum of two or more other reactions, so smaller reactions essentially, the delta H for the overall process is the sum of the delta H values of those reactions. So in other words, once again, it doesn't matter whether you do the reaction in one giant reaction or whether it's a series of smaller steps. The only thing that matters with enthalpy, because it's a state function, is the initial and the final values. So in other words, the energy at the beginning and the energy at the end, okay? So when we are trying to figure out the delta H, if we can't figure out the enthalpy change experimentally, maybe because you can't carry out a reaction all in one giant step, or maybe a scenario like this where carbon monoxide is produced in combustion, but then converts to CO2 once it reacts with oxygen in the air. Because of that, if we need to figure out the delta H, we can look at the delta H and determine that using this concept of a multi-step reaction, essentially. Okay, so what does that look like? If I wanted to state that, I could write it like this. So this isn't necessarily a formula, but this is just sort of, again, a visual representation recognizing that the sum of the delta H's of one giant reaction versus the sum of the delta H's of separate reactions will ultimately be equal at the end of the day because enthalpy is a state function. So what do Hess's law examples look like? What they will look like is they will always be formatted similar to this, where you're going to have what I'll call a desired reaction. So in this case, our desired reaction is we're trying to form 1 mole of SO3, so we'll write that out. And then you're going to be given a series of smaller reactions, like what we see here, and we have to essentially arrange these equations to give us this desired reaction. Okay, so let's first get our desired reaction. Sometimes it'll already tell you the reaction, other times it doesn't. So in this case, it doesn't. So let's write our desired one first. So what would the formation of 1 mole of SO3 from its elements look like? Well, the elements are sulfur and oxygen. So sulfur is not diatomic, so we're just going to write that as S. And sulfur is a gas at room temperature. Plus, oxygen is the other element, but when oxygen is on its own, it's diatomic, so O2. And we're forming 1 mole of SO3. So our product is SO3. That is a gas. It's okay if you didn't know that. But the one key piece here is because we're forming 1 mole of SO3, we cannot change the number here. So we're going to have to think carefully about what coefficients need to go there. And as you'll see, we're going to end up with fractional coefficients, okay? Because I have 1 sulfur here and 1 sulfur here. That works. But unfortunately, I have 2 oxygens here and 3 oxygens there. So typically, if we were balancing this, we would take them both to 6. But since this has to stay a 1, the only way that I can make 2 equal 3 is if I multiply this 2 by 1.5, or in other words, 3 halves, okay? So you can either write that as 3 halves, or if you'd rather, you can write that as 1.5. Either would work, okay? But now at this point, we have a balanced reaction. This reaction here is the one that we're trying to ultimately end up with. We want to know what the delta H is for this reaction, okay? So here's what we do in a Hess's law problem. We need to find where this sulfur is coming from these 2 reactions, where the oxygen gas is coming from these reactions, and where the sulfur trioxide is coming from these, okay? The only things we can do to these reactions are either flip the direction, which would flip the sign, or we can multiply or divide any of these coefficients, which would then likewise multiply or divide the delta H value, okay? So here's what I do. I start at the left in my desired reaction and go through sort of just left to right here. So where is my sulfur gas coming from? The sulfur gas is coming from right here. This is the only place. Oops, sorry, that should be a solid. My mistake. Okay, so our sulfur solid is only coming from right here. It doesn't show up anywhere else in the reaction on its own. I want 1 mole of it as a reactant in my final reaction, and that's exactly what I have here, 1 mole as a reactant. So what I'm going to do is off to the side of this, I'm going to write keep, just to remind myself that I'm actually keeping this first reaction exactly as is. So I am going to rewrite that reaction, because what we'll see is the way we can double check that our setup actually works is involved after we copy these down, okay? So I'm going to keep that first reaction exactly as is. We've used that one now. And that took care of this. Then I look and see my oxygen. Now the problem here is oxygen gas shows up in this one and this one. So if you have something that shows up in both reactions, I wouldn't necessarily do anything with that yet. Just sit tight and it'll end up working out on its own. So let's skip to this. Where do we see our SO3 gas? SO3 gas only shows up right here, but there's a problem. I want 1 mole as a product, but here I have 2 moles as a product. So what I'm going to do is if I want 1 mole in this reaction, that means that I'm going to need to divide this whole reaction by 2, okay? So if I divide that whole reaction by 2, let's write what that would look like. 2 SO2 gas would become just 1 mole of SO2 gas. O2 gas would become half O2 gas. And then our product would be just 1 mole of SO3 gas. Now, because we divided all of our coefficients by 2, if I have half as much material, that's going to be half as much energy change as well, right? So if we divide that by 2, that negative 197.8 is going to become negative 98.9 kilojoules, okay? So when we go to do our work here, if you're now trying to figure out the delta H of your whole reaction, what we do is we essentially add these together. So let's see if when we add these 2 together, we actually get our desired reaction up here. So what I'm going to do is cancel things out that show up the same on both sides, kind of like what we did with net ionic equations. So SO2 gas cancel out. I also see that even though these aren't going to cancel, these will add together. So what I'm left with is solid sulfur, 1.5 moles of gaseous oxygen, and on the product side we have 1 mole of SO3 gas. Notice that these 2 are in fact the same. So because we know that these 2 do add up to our desired reaction, to get our final answer, all we do is now add together our delta H values. So if we add these 2 together, we see that our delta H for this first example would be negative 394.7 kilojoules. Okay, as far as sig figs are concerned, we are adding together, which is why I kept 1 decimal place in both of these. If you wanted to be very cautious throughout, we could have technically made that 4 significant figures there because of the negative 197.8 having 4 significant figures when we divided, but either way, when we add together at the end, 1 decimal place is still our limiting value, so that's why I kept 1 decimal place in my answer. So that's example 5.8. All right, so in example 5.9, same idea. First thing we need to figure out is what's our desired reaction that we're trying to figure out the enthalpy for. So it says we're supposed to use Hess's law to determine the enthalpy of formation of 1 mole of nitrogen monoxide from its reactants. So once again, there are 2 reactants that our elements must be nitrogen and oxygen. Just be careful how you write them because they are both diatomic. So our desired reaction in this case would be nitrogen gas plus oxygen gas forming 1 mole of nitrogen monoxide gas, okay? Now when we balance this, again, remember, we have to keep 1 mole on the product side, so that means we have to put halves in front of both of these, okay? So again, you will see fractional coefficients in thermodynamics. So we're trying to figure out what is the delta H of this reaction. So in other words, we need to make these 3 reactions add up collectively to this, okay? So once again, let's go through. First off, starting at the left, where is the N2 gas coming from? N2 gas only shows up right here, so let's see if it looks like we need it. We need it to be a reactant, and we need half a mole. Well, it is a reactant, but we have the wrong coefficient. So what I need to do is if I have 1 mole here, I need to divide this entire reaction by 2 because that's going to give us the coefficient we need. So if I rewrite that, there's my reaction after I've divided all the coefficients by 2. And then remember, if I divide the coefficients by 2, negative 91.8, needs to be divided by 2 as well. So that would give us negative 45.9 kilojoules. Okay, so that took care of the nitrogen. So now on to the oxygen. Where do I see O2 gas? I see O2 gas here, and I see O2 gas here. So I don't actually want to decide about the oxygen yet, because sometimes it's tough depending on which one you have already to figure it out. So we're going to skip that and come back to it. So we're looking for elements or compounds that are isolated. So let's skip to the next one. Where do we see nitrogen monoxide gas coming from? Nitrogen monoxide gas is only showing up right here. So let's make it look like we need 1 mole as a product. Here it's a product, but I have 4 moles. So I need to divide all of this reaction by 4 to get the correct coefficients. So if I rewrite that, we get this. And our delta H, if we do negative 905.2 divided by 4, is going to give us negative 226.3 kilojoules. Okay, so there we are. Now we have seemingly dealt with everything we need, but we still have this third reaction that we haven't done anything with yet. We didn't do this one. So why do we have this third reaction? We have this third reaction is because what we're going to see is if we try to cancel things out here, we're going to have some extra things left over. So if we try to cancel things out here, what I'm going to see is that these ammonia gases cancel, but at this point, nothing else cancels. So which ones do we actually want in our reaction? We want this one, so we want that to stay. We want the nitrogen monoxide gas to stay, but we have an issue. We want this to go away. We want this to go away because they're not showing up in our final reaction. And we need oxygen gas, but not 5/4. We only want a half, right? So that means we need to use this third reaction to cancel those things out, essentially. Okay, so how can we make that happen? Well, I have water over here as a product, and I realize I forgot the state of matter on that one. There we go. So we have water over here as a product, meaning if we want it to cancel, we need it to be a reactant, and we need 3/2 of it. So here I see it's a product, so I'm going to need to flip this reaction to make it a reactant, but I'm also going to need to multiply it by 3/2 or 1.5 to make that coefficient cancel, okay? So next to this reaction, I'm going to write flip as a reminder to ourselves that we're reversing the reaction, and we need to multiply by 3/2 or 1.5, okay? So if I rewrite that, I would now have 1/2 or 3/2, or excuse me, 1.5 or 3/2, whichever one you like better is fine, of gaseous water as a reactant now, and then on the product side, we're going to have what previously were the reactants, but multiplied by that coefficient 3/2. Now 1/2 times 3/2 would give us 3/4 of oxygen. If you don't like the fractions, use decimals, that's perfectly fine. Our delta H will now become positive because we're flipping it, and then 241.8 multiplied by 1.5 is going to give us 362.7 kilojoules. Okay, so now if we take a look at this, everything should cancel and we can add this up. So what do we see now? We see that our 3/2 water cancel. We also see that 3/2 hydrogen gas on the reactant and product side cancel, and 3/4 oxygen crosses out completely, and 5/4 minus 3/4 leaves us with 1/2, which is exactly what we were trying to find. Okay, so when all said and done, we do have the reaction we were looking for. 1/2 mole of nitrogen gas, 1/2 mole of oxygen gas, and on the product side, the only thing we had left was the nitrogen monoxide. So to get our final delta H value then, all we do is add up all 3 of these. So if we add all of those up, they all have 1 decimal place, so we should keep our answer to 1 decimal place. We find that our answer is positive 90.5 kilojoules. So that means that this process would be endothermic because we have a positive delta H value, and that would be our overall enthalpy change for this reaction here. At this point, you should be able to try homework 4. It is some questions from the textbook as well as one of the worksheets at the back of the notes packet. Good luck.